Hi everyone, my name is Amirul and welcome to our presentation. Today, we are diving into one of the most powerful concept in calculus, which is differentiation. Yes, we will explore what is actually the essential technique used to solve calculus problems. So, what exactly is differentiation? At its core, differentiation is the process of finding derivative of a function. Basically, the derivatives represent the slope of the tangent line to curve at any given point. In real-world terms, it measures the instantaneous rate of change. How fast a dependent variable, which means y, and change with respect to an independent variable, which means x. So, at this, we mathematically denote this as dy over dx or f prime x. To find the derivative efficiently, there are several core techniques of differentiation. Let's review the main one that you need to know. For the first technique is the power rule. For the second technique is the constant multiple and different rules. For the third technique is the product rule. The fourth technique that you need to know is the quotient rule. And the last technique is the chain rule. Mastering the techniques allow us to solve the complex function, which brings us perfectly to our next problem involving implicit function. So, let's look at the solution.
Okay, now for my part, that is question 2a. For question 2a, we must find dy over dx for the function y equal to ln x to the power of 4 cosine of 2x minus 5. For question 2a, we have two different functions multiplied together here. Whenever we see functions that are multiplying, we must use the product rule. Because you can just take their derivatives separately, you have to combine them systematically. For our first steps, we can separate the u and v from the multiplied function. For u, we can make it easy by using the logarithms laws to bring the power down, making our u becomes 4 ln x. For its derivative u prime, it is just 4 over x. Next, for v, it is cosine of 2x minus 5, and for the derivative, we can find it by applying the chain rule, so the v prime becomes negative 2 sine 2x minus 5. Lastly, we can find our dy over dx by applying the product rule formula, that is the first function u times the derivative of the second, that is v prime, plus the second function v times the derivative of the first, that is u prime. We insert the u and v and u prime and v prime, we multiply it, simplify it, and then we got our final answer, that is negative 8 ln x sine 2x minus 5 plus 4 cos 2x minus 5 over x. Okay, now let us move on to part B of question 2. This time we are given one function that is being divided by another. The function is y equal to 3x squared minus 2 over sine x. For fractions, we must use the quotient rule. It is similar to the product rule, but because it is division, we subtract the terms in the numerator and we divide by the bottom square. Okay, next, let us list our pieces first. The top function, that is u, is 3x squared minus 2. We can use power rule to determine our derivative, that is u prime, and we got our 6x. The bottom function is v, that is sine x, and as we know, the derivative of sine x is just simply cos x. For the final part, we can now apply the quotient rule formula. The quotient rule formula, that is dy over dx equal to v u prime minus u v prime over v squared. A great memory trick for this is bottom times derivative of the top minus top times derivative of the bottom all over the v squared on the bottom. Now, we can finally include our pieces into the formula. We put the pieces into the formula, we simplify it, and then we got our final dy over dx, that is 6x sine x minus cos x bracket 3x squared minus 2 bracket over bracket sine x bracket squared.
Now, let's move on to question 3. We are asked to find dy over dx using implicit differentiation. We use this method because y is abandoned inside the function and cannot be easily isolated on one side. To solve this, we will differentiate every term on both sides with respect to x. Whenever we differentiate a term containing y, we must multiply by dy over dx due to the chain rule. Let's break this down term by term. First, the derivative of e the power of y with respect to s is simply e power of y dy over dx. Second, we have a highly composite term, which is sine power of 2 open bracket x power of 3 plus non y close bracket. We apply the chain rule starting from the outside power layer, moving to the sine layer, and finally the inside bracket. This yields 2 sine open bracket x power of 3 plus non y close bracket multiplied cos open bracket x power of 3 plus non y close bracket multiplied by the derivative of the inside, which is 3x to the power of 2 plus 1 over y dy over dx. To keep our equation clean, we can simplify to sine theta into the double angel form, which is sine open bracket 2 open bracket x power of 3 plus long y close bracket. Third, on the right side, we apply the product rule to 4xy. This given us 4xy dy over dx plus 4y. Now, let's substitute this component back into our equation and distribute our terms so we can easily see our dy over dx variable are hidden. As you can see, we now have 3 separate terms that contain dy over dx. So our goal now is isolated dy over dx. We shift our term containing dy over dx to the left hand side and move everything else to the right hand side. Next, factor out the dy over dx from the left side, leaving us with a large bracket expression. Finally, we divide both sides by that bracket expression that we have. To make our final fraction look polished and get rid of the fraction within a fraction, we multiply the entire numerator and denominator by y. And there we have it. This is our final implicit expression for dy over dx.
Now I will continue with the question 4 given to us. The question 4 is use linear approximation to estimate the value of the numbers given correct to 2 decimal places. First and foremost, before we start our solving, we need to find the same numbers that we could replace with x. So we can put the whole thing into the formula later. Here we'll choose 4.05 to replace it with x. However, before we start our differentiation, we need to get rid of the fraction at 16 over x. After we do so, we'll have with 16x power of negative 1. Now, we have our unknown, which is x. We can finally start differentiation, and with that, we'll have our answer, which is 3 over 2x power of 1 over 2 plus 16 over x power of 2. Before we move on to our next step, we need to determine the dx or the delta x, which we could get by subtracting x with x naught, with x being the number that we replaced earlier and x naught is the number that we chose that is close to the number given. In this case, we'll choose 4. By subtracting x with x naught, we'll have our answer, which is 0.05. Now, we can put all the information that we got from the question into the formula given to us. After we calculate them, we will end up with answer 4.2. But since the question wants us to put our answer into decimal place, we need to put our answer as 4.20.
For the last part of this video, I just want to say that mastering the various techniques of differentiation is really crucial for solving calculus problems effectively, whether we are using the power rule, the product rule, the quotient rule, or even the chain rule. Each of these techniques provides a unique tool to find the instantaneous rate of change. Ultimately, these methods allow us to model, analyze, and optimize real-world systems across science, engineering, and economics. Before we finish, I want to express my sincere gratitude to our lecturer, Sir Shawal, and my fellow teammates for their guidance and collaboration throughout this project. Thank you all for your time, attention, and support today.